Descartes famously said, "I think, therefore I am." And in doing so, it advocated a view that the mind and the body are wholly distinct. And this Cartesian dualism often shows up when we think about interacting with computers. People often tell me that they wish they had an interface that provided a direct interaction with their brain. And the intuition here is that your brain has lots of ideas that somehow we just can't get out through our bodies. And it's absolutely the case that we have lots of thoughts that are hard to get out or act out or express. But I want to push back a little bit on the intuition that the problem is the bodily channels for passing those thoughts through. Our brains and our bodies evolved together. The organization and function of the brain evolved in response to our bodily capacities and vice versa. What this means is it's not like there's a massive chunk of cortex somewhere in here that's got no output, like a computer with an empty port in the back just waiting to be connected. There'd be no reason to evolve a brain that had all this empty cortex. And furthermore, keeping the brain functioning is extremely energy intensive. To have an unused part of the brain would be a total waste, which you're welcome to remind your teenagers anytime they're watching television. This mind-body integration runs really deep. Here's an image of the homunculus. It illustrates the sensory motor cortex and how much cortical real estate is devoted to different parts of the body. One thing that really jumps out is the amount of cortical real estate that's devoted to our hands. That's a really high bandwidth channel. Our mind-body integration doesn't mean that there's no room for improvement or that all input technologies are equal. Let's look at a powerful but mundane example, the keyboard. In English, the top row of the keys along the keyboard spells QWERTY. As many of you probably know, the QWERTY keyboard design emerged in response to a mechanical challenge. With a typewriter, you've got the hammers that are attached to each of the keys so that when you press on a key, that's flipping a hammer which has a letter on the end of it that's going to hit the sheet of paper that you're typing on. If the user types adjacent keys on a typewriter, that springs adjacent hammers into action, and while one's going down and the other's going back, they can jam. This QWERTY typewriter layout was invented in the early 1870s by Christopher Latham Scholes. It solved the hammer collision problem by drawing on a wonderful combination of computational analysis and iterative design with users. In English, and in all languages, some characters appear more often than others. In English, the letter forms earning the most airtime are E, T, A, I, O, N, S. E is the most common letter, followed by these. Furthermore, some pairs of letters, called bigrams, appear more commonly than others. Scholes' collaborator, Amos Densmore, tallied the bigram use in the King James Bible and found the following letter pairs to be especially common. Scholes' innovation, like somebody seeking to break up a bar fight, was to take these letter pairs that co-occur, put one on one side of the typewriter keyboard, and the other on the other side of the typewriter keyboard. You may have heard that the QWERTY keyboard design is not very efficient, After all, it was created to solve this mechanical problem that no longer exists. Economists describe technologies and decisions whose design reflects historical constraints rather than current reality as path dependence. I think that the last time I used a mechanical typewriter was filling out a graduate school application form. And while jamming hammers would make a great funk band name for fast typists, it's not a major problem in my life. So we have a layout that was designed expressly to combat the problem. Furthermore, we have a layout that was designed expressly to combat the problem of speed. People type quickly, the hammers jam, and you got a problem. So this can't be a good design, right? Actually, no. Physically separating the hammers to remove mechanical collisions also temporally separated the hand rolls to reduce biomechanical collisions. What I mean is this, that as I'm typing like this, one hand is going down hitting the first key, and the other hand can be preparing to hit the next key. And this alternation, one down while the other goes up, is actually an extremely efficient design. The QWERTY keyboard is just one example of data-driven layout based on usage frequency. Lead-type printers for English newspapers favored a frequency-based arrangement, this ETAIONS. And when they made a mistake, typesetters for the newspaper, they would run their fingers across the row that began with S. In fact, that row is SHRDLU. Run your finger across this a few times as a warning that there's a typo that needs to be fixed. But of course the typo, or the warning, didn't always get pulled out of the lead that came out of the machine. Every once in a while, this would actually end up in the newspaper. It's like the lorem ipsum that shows up on so many web pages of the analog age. Mad Magazine thought this was funny, and so they would put it in their magazine from time to time. And the famous computer scientist Terry Winograd took up this joke as the name of his seminal natural language understanding system, which he called Shrdlu. These first two examples both come from English, but of course they also apply to other character sets. One of the most interesting examples is Chinese with its myriad logograms. Here's an example of a Chinese typewriter that has more than 25 characters placed within it. When these characters were typeset by people, especially, for efficiency purposes, the most frequent letter forms were placed in the middle of the job tray, the big wooden box that contains all the characters. And what the historian Thomas Mullany pointed out to me is that then you can use the layout of the job tray of all of the characters as a means of understanding the frequency of character use in the language. And one really interesting example of this is if you look at job trays from the early 20th century in China, the character Mao was present in the periphery of the tray, if at all. Of course, 50 and 60 years later, that character was much more central to printing in China. Today, we describe the system used by all of these examples as one of optimization. None of these keyboards had the benefit of computers or formal optimization algorithms to decide the best layout. The data was tallied manually, and the iteration was trial and error. If we did have the benefit of modern computation, how much better could we do? Shuman Jai and colleagues have spent a decade investigating computationally designed keyboards. It draws on motor models like Fitts' law that you learned about in the earlier videos. If we know from Fitts' law how long it takes to acquire a target, here, how long it takes to press on a key, and we know from language models how frequent those different characters and character combinations are, then it's in principle possible to design a keyboard that minimizes the total amount of travel that a typist must engage in. And this is exactly what Schumann and his colleagues did. Now, for many of us, desktop keyboards are fast enough most of the time for practical purposes. It's clearly possible to find a keyboard that's slightly faster. In fact, several designs exist. You may even use one. But the benefits are relatively modest, and desktop typing speeds are generally sufficient. You know, for a good touch typist, the barrier is usually coming up with stuff worth typing. By contrast, input on mobile devices is a heck of a lot slower, even for your 17-year-old who's got the Olympic rate thumb movement. So if you want to make a big impact in user interface design and convince people to switch, it's best to look for a place where there's currently a lot of pain. Consequently, the literature has hundreds of examples of different mobile keyboard designs. And I'd like to talk about Schumann's work today because I think it's the next insight after just the computational layout that's the really transformative one. Because a better layout of keys can significantly improve layout on a mobile device, but embarrassingly, we're kind of entrenched and used to what we have. Also, even if we move the right characters next to each other in the right ways, in a character-by-character entry system, I still need to put a digit down on one key, raise it up, and put it down on another key. Or in a two-thumb or multi-finger system, I can oscillate back and forth. What if you didn't have all of that up and down? That would really speed things up significantly. So that's what Schumann did, is if you were able to put your finger down at the beginning of a word, or stylus down at the beginning of a word, go through all of the letters that you might touch, and then release at the end of the word, that's what Schumann's ShapeWriter system did. And this word-based entry system opened the door for many subsequent innovations. You've probably even tried some of these. And I think it's a really interesting example of how, especially once your input device is computationally rendered at every frame, and you have lots of smarts underneath the hood, there's some really radical transformations of input devices that are possible. The last example that I want to show today comes from Jacob Wabrock and his colleagues. Desktop keyboards and the QWERTY design are relatively entrenched in English. In the mobile world, we have some more flexibility for something like a word-based input system to really come and take things over. Another group of users for whom input is extremely difficult and slow are users who have motor impairments. In fact, all of us have motor limitations, and some more so than others and of different sorts. And so there's a big opportunity there. EdgeWrite used a stylized alphabet system, similar to what there was a system called Graffiti for the Palm Pilot. And the innovation of EdgeWrite, it was a piece of plexiglass that provided a square hole through which you would enter with a stylus or finger. Now, what's nice about this is it offers a physical constraint. So if I have to draw a straight line, I'm not very good. That's one reason we use a ruler when we need to. The EdgeWrite system gives you that physical constraint. And what that means, especially for users with mobility limitations, is you can lean against the sides and enter a lot more quickly. What we've seen in all of these designs in this video is that thinking about what people are going to type and who's going to be doing the typing and what the setting for the typing is can give you new innovations in how input design layout works to create a much more fluid, fast, efficient experience.